Okay, so this is the lecture for algebraic identities, lecture number 4. And as usual, after this lecture, I will upload the video file and you will find a link to the PDF file to a problem set. It would be very useful if you try to solve those problems by the next week. Okay, so I want to introduce a new, very simple identity in the beginning. It's a very simple identity, but very useful one. So the identity is this: if I have x plus a and multiplied by x plus b, yes, it's very simple. I have a binomial multiplied by another binomial. There is one expression in common, so here x is in common. And if I want to multiply them, of course, this is so simple that you can just multiply. But if you multiply it, then the answer would be the common term to the two, and then plus the sum of these two terms multiplied by the common term, x, and then plus the product of a and b. Yes? So it's very, very simple. Yes, why? Because if I start multiplying this, it becomes x squared plus xb plus ax and finally plus ab. Yes? And then you see that in these two middle terms, I can factor x out. Yes? So what happens, this becomes x squared plus a plus b x plus ab. Yeah? It's useful to know this identity, this simple identity in this form. Okay, so let me give you some examples. So use this identity to expand. Okay, so number one, for example, x plus 3 times x minus 1. Okay, so if I want to calculate, if I want to expand this, of course I can use this identity. Why? Because I have two binomials multiplied by together, and then one term is in common. Yes. So what can I do? I can write it as the common term to the two plus these two terms added together. So 3 plus minus 1. The first term here is positive 3. The second term is negative 1, multiplied by the common term, which is x. And then at the end, I multiply these two terms together. So it is 3 multiplied by minus 1. Okay, so this becomes x squared. 3 plus minus 1 is 2. 2 times x is 2x. And then I have minus 3. So that is a very simple task. Okay. Okay, let me give you one more example, at least of this type. So number 2, 2ab3 minus c squared multiplied by 2ab to the 3 plus 4c squared. Yes. So I also, for example, I want to multiply these two binomials together. Again, you see that this term is in common in both of these brackets. Yes. So according to this rule, it is the common term. X is the common term in this identity. Common term to the two. So it becomes 2ab cubed to the 2. And then plus the sum of these two terms minus c squared on one side plus 4c squared on the other side multiplied by the common term, which is 2ab cubed. And then finally, I multiply these two terms. So plus minus c squared multiplied by 4c squared. Yes? And since we are supposed to expand, I have to continue until I don't have any brackets, any pairs of brackets left. Okay, so this is simple. So this becomes 4a squared b to the 6. And then if you see here, 4c squared minus c squared is 3c squared. So let me write here. This is 3c squared. And then if I multiply 3c squared by 2ab cubed, 3 will be multiplied by 2, so it gives me 6. And then I will have a b cubed c squared, yes. And then finally, minus c squared, and then multiplied by that, it becomes minus 4c to the 4. Yes, so it's very simple. Okay, let me give you a little bit more interesting example. So number 3, for example, what can we do if I want to calculate this, for example, x plus 2y minus 1 multiplied by x plus 2 minus 3y. Yes? Okay, so here what you can see is that there is only one term here which is in common. Yes? This is x, and of course these two terms are not in common. But I can use the same identity. So I can say that the common term to the 2, so it becomes x to the 2, plus these two terms added together multiplied by the common term, which is x, plus the product of these two terms. Yes, so it is 2y minus 1, 2 minus 3y. But of course, here we cannot do much. We have to simplify. So this is x squared, and here 2y minus 3y is just minus y, and then here minus 1 plus 2 is a positive 1. So this becomes positive 1 minus y multiplied by x. Then I will have 2y minus 1, 2 minus 3y. And then, of course, I cannot do anything more, so I have to multiply. So then it becomes x squared plus x minus yx. I am multiplying x inside, and then I have to multiply these together. So then it becomes 4y minus 6y squared minus 2 plus 3y, yes? And I can simplify this a bit more, so it becomes x squared, and then I have plus x minus yx. But this term and that term, I can write 7y, and then I have minus 6y squared minus 2. So I cannot simplify more than that. Okay, I will give 2 more examples here, and then I will go to the next topic. Okay. Okay, so the next one is this example. X minus 1, x minus 2, and then I have this situation, x squared minus 3x to the 2, and then I have minus 2, x squared minus 3x, and then plus 4. Okay, I want to expand this expression, but of course I want to use the identities as much as possible. Not exactly only this identity. We had some identities from the previous sessions we want to use. Okay, so for example here, this is this new identity, yes? What can I do? I can write the common term to the 2. Now we can do it in our head now. The sum of these two terms is minus 3, and then multiply minus 3 by the common term, so it becomes minus 3x. And then I multiply these two terms, it becomes positive 2. Yes, this is the new identity we just learned. Okay, but let us not simplify this for the time being, because I hope that you can catch the pattern yourself now. Yes, can you see the pattern now? Okay, so if you see, do you remember we had some identity like this? It was a plus b multiplied by a squared, the product of them with the opposite sign, and b squared. If we have this kind of pattern, the answer to this identity, if you remember from the previous video, it's a to the 3 plus b to the 3. Yes, and then you can see immediately this is happening here. If I consider this one term and consider this another term, this term to the 2 appears here. Yes, so let me write it in this form. This is box to the 2. And then circle to the 2 also happens here. This is circle to the 2, yes? And then this is the product of these two terms with the opposite sign. Yes. So this, if you see, this is exactly this pattern. Yes. Okay. So if I want to calculate this, if I use this identity, the answer to this becomes equal to the first one to the 3 plus the second one to the 3. Yes. Okay, and then if you remember, we learned some identity for this. I have a binomial, I want to raise it to power 3, yes? So what can I do? It is the first one to the 3, which is, let me write everything. X2 to the 3 plus 3 times the first one to the 2 multiplied by the second one, which is minus 3x in this case, and then 3 times the first one itself multiplied by the second one to the 2, and finally the second one to the 3. Yes, this is the expansion of this first part, and then I have 2 to the 3, which is 8. So I put 8 at the end. Yes, and we can simplify this, of course. X to the 2 to the 3 is x to the 6. X to the 4 times x is x to the 5. And then I have minus 3 and 3, which is minus 9. Here, minus 3 to the 2 is positive 9 multiplied by 3 is 27. And then I have x to the 2, which becomes x to the 4. And then here I have minus 27, minus 3 to the 3 is minus 27, x to the 3, and finally I have 8. Can I simplify more? No, because all of them have different powers and they are not actually, they are not similar. Okay, one more example here. So for example, I want to expand this x plus 1, x plus 2, x plus 3, x plus 4, and finally plus 1, for example. Assume that I want to simplify this. Okay, of course, you can see that I can use this identity we just learned here, and the same identity, we can just use them here. And if I do that, let us see what happens. If I do this here, then it becomes x to the 2. I add these two together, it becomes 3, and then multiplied by the common term, and then I multiply these two, it becomes 2. If I use the same identity here, it becomes the same story. So it becomes x squared, and then the sum of these two numbers becomes 7, and I multiply it by x, it becomes 7x, and then this becomes 12. And then if I want to multiply this by that, still I can use the same identity, but this time x squared is in common, yes? This is one way, of course, that is not wrong, you can just do it, but I would prefer to do it in a different way. How? For example, these are 4 numbers that I am supposed to multiply them. So it doesn't matter if I multiply this one by this one first and find the result and multiply the result by the next one. Or if you want, you can multiply these two first and these two together. Yes? Let us see why this is better. If I multiply this by that, this is exactly equal to, this is the identity we just learned, yes? So this becomes, again, this x is in common, so this becomes x squared. 1 plus 4 is 5 multiplied by the common term. And then finally, 1 times 4 is 4, yes? Agree? And now I can do the middle terms. What happens in the middle term? So x and this is the common term to the 2. The sum of these two numbers, which is 5, multiplied by the common term. And then I have 2 times 3, which is 6. And I have, of course, 1 at the end. Yeah, so I can put this equality. Yes? But this is better. Why? Because now the common term, you have more common terms. Yes, it's better. So then again, using the same identity, the answer of this product is the common term to the 2. Sum of these two numbers, which is 10, multiplied by the common term, which is this one, and then multiplication of these two terms, which is 24, and then I have 1 at the end. Okay. So the question here is to expand this expression. So if I want to expand this expression, I have to use the quadratic rule here. So this becomes x to the 4 plus 2 times the first one times the second one is 10x cubed, and then the second one to the 2 is 5x squared. And here I can multiply 10 inside, and then 24 plus 1 is just 25. Can I simplify this more? Yes. So I can write it as x to the 4 plus 10x to the 3 plus 15x to the 2. I just combine these two terms. And then I have 50x plus 25. Yes? But you might say that, okay, why we should do it in that way. Of course, there is no obligation to do it in that way. But you see, I want to tell you something. In the future that I want to teach you about factorizing polynomials, if you do it in the way that I did, not in that way, you can immediately see a pattern emerging. Yes, this is the topic of the next lessons. We will talk about factorization later. But you see here, if I combine these two terms here, what I'm saying is that the solution to this problem by expanding is only this one, because I have to remove the brackets. But I want to tell you that what is the advantage of this way of thinking. In the future that we want to factorize polynomials, I hope that you can immediately detect a pattern in this form, yes? Because 24 plus 1 is just 25, yes? You see, if in your head you take this one, the box, this becomes box to the 2, and this is the box, and this circle is 5, because 5 to the 2 is 25. And then it becomes immediately clear that this is x squared plus 5x plus 5 to the 2. Yes? Why? Let us check. By quadratic rule. The first term to the 2 is this one. 2 times the first one times the second one is exactly this one. And then this one to the 2 is 25. Yes? So it means that I can remove these brackets. They are not necessary. So what you can see is that this expression is equal to this expression to the 2. But you see that this expression is not in the product form because of this plus 1, but this expression is in the product form. So it means that you are able to factorize that if you look at the problem in this case. But of course, factorizing polynomials is the topic of the few next lectures. But the answer to this question here is just this one, because we are supposed to expand, not to factorize. Yes, okay. Now I want to introduce one more identity here now. Uh, okay, so the identity I want to introduce here is if do you remember we had this from before? We had a plus b to the 3. We had this identity that this is a to the 3 plus 3 times the first one to the 2 times the second one plus 3 times the first one times the second one to the 2, and finally we had the second one to the power of 3. Yes. Now I want to see that what happens if we have 3 terms to the 3. Yes. So this is the identity that I want to introduce today. A plus b plus c to the 3. It turns out that you can write a to the 3 plus b to the 3 plus c to the 3 plus c times a plus b times b plus c times c plus a. Yes, so this is the identity that I want to introduce today. Yes. Okay, so if you want, let us compare a little bit before proving this. Let us compare this identity with that one. In this identity, a plus b to the 3 is equal to. If I rearrange the terms, I can write a3 plus b3 next to each other. Yes, and then I can factor 3 and ab out from here. So 3ab times a plus b. Yes, this was what we learned before. Yes, do you remember? Okay, and then you can compare it with this situation. In this situation that we have 2 terms to the 3, we have the first one to the 3, the second one to the 3. plus 3 times the first one times the second one times the sum of them. But this is a slightly different. So if I have a plus b plus c to the 3, it becomes the first one to the 3, the second one to the 3, the third one to the 3, and we have this 3, but we have this combination, a plus b times b plus c times c plus a. Yes, and of course, if I want to prove this one for you, I can do something. I can expand this by any way that I can do, keep it somewhere, expand this one and compare them, okay? But instead of doing that, let me just try to do it in another way. So I want to prove this identity for you here. But do you remember we had this? If you remember, I can move this to the left-hand side, so it becomes a plus b to the 3. Then it becomes minus 3ab, a plus b. It becomes equal to a to the 3 plus b to the 3. Yes? And in this identity, let me replace b with minus b. Because this is an identity, it is valid for all possible values. It's also valid for if I change b to minus b. If I change b to minus b, what will happen? This becomes a minus b to the 3. Yes. Then this becomes positive 3ab. This becomes a minus b. And on the right-hand side, this becomes a to the 3 minus b to the 3 is minus b3. Yes. Okay, so let me write it as box and circles here because I want to use them here. So here instead of a, I put a box to the 3. Instead of b, I put a circle, so it becomes circle to the 3. And I do the same thing on the left hand side, and I write it on the right hand side here. So this is square minus circle to the 3 plus yes. So this is what we got. This is actually more or less we learned in the previous lecture. Okay, so let me emphasize again. If I want to prove this, you can just expand this by multiplying it 2 times and then 1 more time and keep it, and then expand this one and compare them term by term. But instead of doing this, let us do it in a more nicer way from my perspective. Okay, so let me calculate this one for you. So proof. I would consider this expression. So it is a plus b plus c to the 3 minus a to the 3. Yes. Let us consider what happens if I want to calculate this. Okay. I want to use this to expand this. So let me take this one to be the box. Let me take this one to be the circle. And I want to use exactly this identity. So what will happen? This becomes equal to the box minus, box is a plus b plus c, minus a, totally to the power of 3. Yes. And then I have plus 3 times the box, which is a plus b plus c, times the circle, which is a, times the box minus the circle. Yes. Agree? So I have just assumed that this to be the box, this to be the circle, and I use this identity, just replace. But the good point is that this a and this a are cancelled here. So I will get b plus c to the 3. Yes. And then here, this a and that a are cancelled. This a, I can write it next to 3. So it is 3a, a plus b plus c times b plus c. Yes. But now look here, a plus b to the 3 can be written as a to the 3, the first one to the 3 plus the second one to the 3 plus 3 times the first one times the second one times the sum of them. So I will use that one here. So this becomes the first one to the 3, the second one to the 3, plus 3 times the first one times the second one times plus b plus c. And then here, what can I do is that I can multiply this inside. So then it becomes plus. I multiply 3a by this a, so it becomes 3a squared, and then I multiply it by b plus c, and finally I have b plus 3a b plus c times another b plus c, so it becomes 3a b plus c uh, to the 2. Yes. So what I have done, I multiplied this 3a inside, it becomes 3a squared, and then I multiply this one from the right again here, so this becomes this combination. And then I multiply 3a by this b plus c, it becomes 3ab plus c, but another b plus c will come in, so it becomes b plus c to the 2. Okay, but the good point here is that if you see, I can write it as b to the 3 plus c to the 3. Between this one and this one and this one, I can factor a 3, which is common. And I can also factor b plus c out, because b plus c is also common in all of them. So I can take 3b plus c, and what is left for me is bc from the first one, and a squared from the second one. And then here I will have a times b plus c. Yes? Okay. And then what can I do? I can continue a bit. It's b to the 3, c to the 3 plus 3b plus c. Okay? And what can I do? I can multiply this inside, so it becomes, let me write a squared first. Let me multiply this inside, so it becomes ab plus ac plus bc. Yes? I multiplied this inside, and then I wrote this bc there. Yes? But again, this is more or less this new lesson today. So I can write it b cubed plus 3c cubed, and then I have 3b plus c. And then you see I have a squared here. And then if you see, I can factor a out from these two. I will factor it on the right-hand side. So it becomes b plus c times a. And then finally, I have b c. Yes? Okay, can you recognize this last pattern now? Yes? Do you remember we had this identity? We had x plus a, x plus b. Today, we just learned it today. It is x squared plus a plus b times x plus ab. Yes? We had just this one. And if you compare this one, what is happening is that a here will play the role of this x. So you see, this a will play the role of this x. And b play the role of this a, c will play the role of this b. So that's exactly the same expression. So what can I do? I can write as b3 plus c3 plus 3b plus c. And then instead of this whole expression, what can I write? I can write a as the common term, and then I can write b in one of them and c in one of them. Yes. So if you don't believe, you can just multiply it yourself. Yes. A times a is a squared. You can compare it here. A times a is a squared. A times c is ac, and b times a is ab, and then this is also this. But then look here, and this last term. So what we proved is this. Therefore, what we proved is that a plus b plus c to the 3 minus a to the 3 is equal to this expression. And if you don't mind, let me write them in order. I will write a plus b first, and then b plus c second, and c plus a as the third. Do you agree? So I was able to prove this one for you. But then if you move minus a3 to the right, it becomes exactly the identity that we are supposed to prove. Yes? So I move a3 to the right, then I will have this. Of course, you might think that I have complicated the problem a lot. It was much easier to expand both sides and just simply compare them. I'm not saying that this is not working, but if you want to work in these kinds of problems, it is very good to improve your skills to do something like that. Okay, so this is one of those identities. Of course, this identity is not used that much, but let me also give an example. So how can you use this to solve some problems? Okay. Okay. And I can give you one example here. So example, um, let A, B, and C be real numbers such that we have this. We know that A plus B plus C to the 3 is equal to A to the 3 plus B to the 3 plus C to the 3. Prove that under this condition, A plus B plus C to the 5 is also equal to A to the 5 plus B to the 5 plus C to the 5. So our goal is to prove this. If this happens for 3 real numbers, then we want to prove that also the same thing for fifth powers will happen. Okay. Okay, so you might guess that this identity is a good starting point because there is some relation between this expression and that expression. And of course, it is mentioned that they are equal, yes? So what can we do? So here, I can conclude from this identity. What happens? If this expression is supposed to be equal to that expression, then it means that what is left over is actually 0, yes? So you can immediately conclude that 3a plus b B plus C and C plus A is indeed equal to 0. Yes, understandable? This is the general formula. This is valid all the time. Under these conditions, this expression is supposed to be equal to that expression. So it means that what is left over has to be equal to 0. But then I have a product of 4 numbers equal to 0. The first one is not 0, it is 3. So it means that if this product is supposed to be 0 by the 0 product rule, at least one of them has to be 0. So this implies that either A plus B is equal to 0, or B plus C is equal to 0, or C plus A equal to 0. Okay? So let us take 3 conditions. So number 1. So I can call it number 1, 2, and then 3. Yes? So let us consider this has happened. A plus B is 0. Okay, I am supposed to show that this to the power of 5 is the sum of the fifth term. But I think it is easy, isn't it? Because this means that B is minus A. If A plus B is equal to 0, it means that B is minus A. So here, the left-hand side of this identity is A plus B plus C to the 3 to the 5. But A plus B is 0, so it becomes 0 plus C to the 5. Then it becomes just C5. Yes? And what happens for the right-hand side? So the right-hand side is A to the 5 plus B to the 5 plus C to the 5. But instead of B, I can plug minus A. So this becomes A to the power of 5. Instead of B, I plug in minus A to the power of 5. And then I have C to the power of 5. But this becomes A to the power of 5 plus, this is negative to the fifth power, which is an odd number, so it becomes minus A5 at the end. And then C5 is left, yes? But then what happens? A5 and minus A5 are canceled, so what I get is just C5. And then you can see that the left-hand side under this condition is C5. The right-hand side is also C5. So what can I conclude from here? that the left-hand side is indeed equal to the right-hand side. Yes, agree? And then, of course, you need to convince yourself that this also happens when the second condition happening and the third one, but they are completely similar. So I think you can fill the gaps yourself. Okay, now I want to go to the very important identity. Usually this identity is used a lot in the contests type of problems in mathematics, in algebra, okay? Okay, so another identity I want to talk about is this expression. So a to the 3 plus b to the 3 plus c to the 3 minus 3 times abc is equal. This expression can be factorized, can be written as the product of two polynomials, a plus b plus c. I have a squared plus b squared plus c squared minus ab minus bc minus ca. So this is a very useful identity. Yes. So this means that if you want to write this expression as a product, this is the formula. The proof of this is very simple. Yes. So the proof is that I start from the right hand side and expand it, simplify it, and I will get the left hand side. Yes. So let us just do the proof quickly. So if you want to prove this identity, I would say the right hand side is equal to. Okay, start multiplying them. I will multiply them without any further explanations. Yes, I multiply each term by every term there. Yes, so this becomes yes. So I just multiplied them. 3 terms here, and then I have 6 terms here, so there should be 18 terms. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. That's right. Okay, let us simplify that. Okay, I need a3. Do I have it? Yes, I have a3 here. Okay, so let me write it. And not to get confused, let me cross it over. And then I need a b to the 3. I have it here. And then I need a c to the power of 3. Okay, but let us see what happens. I have positive ab squared here. I should also have a negative one. Yes, I have it at the end. Yeah, so this one and that one are totally canceled. ac to the 2. Do I have the negative one? Yes. Minus c2a is the same as ac2. Different signs, they cancel. I have minus a squared b. Where is it? Yes, here. This one and that one is also canceled. And then you see minus ca squared, and this one also canceled. And then I have minus b to the 2 and c. Where is it? It's here. That's also canceled. And then this one will also cancel that one. What is left is minus ABC here, minus ABC here, minus ABC there. So it becomes minus 3ABC, and that is the left side. So the proof is actually very simple. Okay, but the corollary coming out from this identity is the most important one. So let me write a corollary here for you. So do you remember, corollary is an immediate consequence after you prove a theorem, and usually it is worthy to remember. Okay, so corollary. So this is the corollary. A plus b, a to the 3 plus b to the 3 plus c to the 3 is equal to 3abc, if you see the sum of cubes of three numbers is equal to 3 times the product of those numbers, then you can immediately conclude either they are all equal or the sum of them is equal to 0. Okay? And the other way around. So this is if and only if theorem. Yes? I want to talk about, this is the pinnacle actually of this session. I want you to learn this identity. This is used in, as I told you, in mathematical contests, type of theorems, type of problems. Okay, so this tells you that if you see this is equal to 3abc, then you can immediately that either all these numbers are equal or the sum of them has to be equal to 0, nothing else. And the other way around. If this happens, this is true. If this happens, this is true. Yes? So this is if and only if part. If you remember, I talked about if and only if. Whenever we have a theorem expressed as if and only if, it has a double side. It is two theorems actually expressed in one theorem. We have to prove both of them. Okay, so what can I do? Let me start from here. I want to prove this direction first for you. Okay, so this is the proof, but I want to go from right hand side to the left hand side. Okay, assume that A is equal to B is equal to C. Agree? I want to show that this happens if this happens. Okay, if A is equal to B is equal to C, then the left hand side of this expression is equal to, I write it as a to the 3 plus, but because B is equal to A, I can replace it by A. And again, because C is equal to A, I can replace it with A again. So what happens? The left-hand side simply becomes 3A to the 3, yes? And then the right-hand side, what is the right-hand side then? So the right-hand side is 3ABC. So I can write 3A, but because B is supposed to be equal to A, I can replace it with A, the same for C. And then if you calculate this again, it becomes this, yes? So you can see that under this condition, this one and that one are exactly the same. So this implies that the left-hand side is indeed equal to the right-hand side. Okay, but do you have any idea what happens? How can I prove this if this happens? Yes, any ideas? A plus B plus C is equal to 0. I want to prove that A to the 3 plus B to the 3 plus C to the 3 is 3 times ABC. And here I can use this identity that I proved here for you. If A plus B plus C is equal to 0, what happens for the right-hand side? If A plus B plus C is equal to 0, regardless of this value here, 0 times this totally vanishes, yes? So by the previous identity, you can conclude that this expression is 0, yes? Because A plus B plus C is 0, 0 times anything is 0, so this means that this expression is 0. So then it implies that A to the 3 plus B to the 3 plus C to the 3 minus 3ABC is equal to 0. But then I move this minus 3ABC to the right, it becomes A to the 3, B to the 3, C to the 3 equals to 3ABC. And this is also done. Agree? Okay. So the proof of one part is finished, the proof of the other part. So now I want to prove in this direction. So what does it mean I want to prove in this direction? This time it means that I assume this to be true. I want to prove that either this happens or that happens, yes? But that is also easy. So I would say that A3 plus B3 plus C to the 3 is equal to 3ABC, yes? This is my assumption now. I want to prove that either that first one happens or the second one. If this is equal to that, then what does it mean? It means that A to the 3 plus B to the 3 plus C to the 3 minus 3ABC is equal to 0. Agree? But then I use again this identity. A to the 3, this expression is supposed to be 0. This is equal to this expression, so it means that this expression has to be equal to 0. So again, I use the previous identity. It implies that a plus b plus c, a squared plus is equal to 0. Agree? Okay, but we don't need this identity anymore for the rest of the proof. Okay, but now can you tell me what to do? This is a product. A product is equal to 0. But again, I can use the 0 product rule. So this implies that either the first one is 0 or the second one is 0. Yes? Okay, what I was supposed to prove, I was supposed to prove that if this happens, either a plus b plus c is equal to 0, which I got it here, or a is equal to b is equal to c. But instead of that, I got this expression. But if you remember algebraic, I don't remember exactly what was the lecture. I think it was the third lecture. If you remember, that is one theorem there, yes? Do you recognize that? I move these 3 to the right. Then it becomes a squared plus b squared plus c squared is equal to ab plus bc plus ca. And I proved this as a theorem that if this is equal to that, you can immediately conclude what? You can conclude that all of them has to be equal the same, okay? So a theorem from, yes, I think that was the previous lecture. I don't remember. A theorem from a previous lecture. Okay, and of course you don't need to recall that theorem. If you don't believe in that, if you have forgotten, you can just do this. Do you remember I multiply both sides by 2, I move everything, and I make 3 complete squares, and the sum of non-negative numbers is equal to 0. It will guarantee this. Okay, so this is a very important fact when you want to solve a little bit harder problems. Okay, so, and if you don't mind, let me write this in this form. So let me use this box, circle, triangle way of writing, okay? Because I want you to see the pattern. So what can I write is that if something in the box to the 3 plus something in the circle to the 3 plus something in the triangle to the 3 is 3 times what is contained in box times what is contained in circle times what is contained in this. If this happens, then you can immediately conclude that either they are all equal or the sum of them is equal to 0. And the other way around. So let me emphasize another arrow. If somebody tells you that this or that happens, then you can immediately realize this. You don't need to calculate the details. Okay, so let me solve some problems for you using this example. Let x, y, and z be real numbers. Okay, prove that x minus y to the 3 plus y minus z to the 3 plus z minus x to the 3 is 3 times x minus y times y minus z times z minus x. Okay, I want to prove this. Of course, you really don't need to know this in the first place. You can actually be patient, raise this to power 3, raise this to power 3, add them, and then put it aside, multiply them, and then compare them, okay? Yes, you can do that, of course, but this is a very nice way to do it. How? In this theorem, if I replace the box with x minus y, and if I replace the circle with y minus z, let us consider that the box is x minus y, the circle is y minus z, and the triangle is z minus x. Yes? Of course, you might say that how should I understand to do this? Yes, little by little, by solving more problems, you will get experience. Okay, now let me ask you one thing. If I add the contents of these box and circle and triangle, what will happen? Let us check. The box is x minus y, plus the circle is y minus z, and then this is z minus x. And then you immediately see that this x and that x are cancelled, this y and that y are cancelled, and the same here. So you will get 0. Okay? So you see that box plus circle plus triangle is indeed 0. And what you want to talk about, you want to calculate box to the 3 plus circle to the 3 plus triangle to the 3, yes? The left-hand side of this identity is this expression. And I know that the sum of these expressions is equal to 0. So then what can I write? According to this theorem, if the sum of these are 0, I can conclude that this is equal to that. So this means that this is equal to 3 because this is 0. This is equal to 3 times box times circle times triangle. But what is box? Box is x minus y, yes, times y minus z times z minus x. So as simple as that. Yes, is that understandable? Okay. Let me solve one more problem of this type using this identity. Example. If x is a real number such that x to the 3 plus x equals to 1, determine the exact value of this expression, x to the 5 plus 1 over x minus 1 x to the 4. Okay, so one way of tackling this problem, probably the most natural one, is try to find x. Okay, but finding x from a cubic equation is not that simple. And even if you know the formula for that cubic equation, you will get a very involved expression if you want to keep the exact value. Yes, and even if you can do this, and raising those numbers to power 4 and calculating this is actually horrible. Yes, so what can we do? This is the trick. I want you to understand this trick. So here, this is given to me. X to the 3 plus x is equal to 1. Agree? X is a number satisfying this condition. So what can I do? I can say that x to the 3 plus x minus 1 is equal to 0. Yes? I move that one to the left. But let me just do it like this. Then this implies that x to the 3 plus x, instead of minus 1, let me write positive plus negative 1. Yes, is equal to 0. Agree? There is no difference between minus 1 and positive negative 1. They are the same. But what is the benefit of that? The benefit is that if you can realize you can take this the box, you can take this the circle, and you can take this the triangle, what you can see? You can see the box plus the circle plus the triangle is equal to 0. If the box plus the circle plus the triangle is equal to 0, if you want, you can conclude this expression. So what does it mean? It means that according to that corollary, the box to the 3, which is x3 to the 3, plus the circle to the 3 is again x to the 3, plus the triangle to the 3 is equal to 3 times the box multiplied the circle multiplied by the triangle. Agree? Okay, so let me keep this and start writing from here. I might need it for the next problem as well. Okay, so then let us continue here. X to the 3 means that this is x to the 9. Yes, and this is also x to the 3. And minus 1 to the 3 becomes minus 1. What is on the right hand side? 3 times x to the 3 times x is x to the 4 times minus 1 is minus 3x4. Yes? So this was not easy to get, because immediately I used that theorem and I got another more complicated expression. But look, here I have this expression. The question mark is that expression. Can you see a connection? You see, this is x to the 9, but I need x to the 5. So I need to divide by x to the power of 4. But I need to convince myself that I can do it safely. What do I mean? I'm not allowed to divide by 0. So I need to guarantee that x is not 0. And of course, x is not 0 because if x is supposed to be 0, I will have 0 on the left and 1 on the right, a contradiction. So I'm on the safe side. X is not 0. So it means that x4 is not 0. So I can divide both sides by x4 safely. But if I divide this by x4, this becomes x to the 5. If I divide this by x4, it becomes x to the 3 divided by x to the 4. And if I divide this by x4, it becomes minus 1 divided by x4. What is left on the right-hand side is just simply minus 3. Yes? And that's exactly what we want. It's x5. You can immediately see that this expression, 3 of these x's are cancelled with 3 of them, and then 1 is left in the denominator. And then the next one is this expression, and that's minus 3, yes? And that's exactly what we are supposed to calculate, yes? So this means that our question mark is negative 3 in this case. Yes? Okay, let me just do here the next one. Okay, so example, this is also a good example. Solve the following equation. Yes, so the equation is this. X minus 1 to the 3 plus x minus 2 to the 3 is equal to 2x minus 3 to the 3. Of course, the first natural step to do might be just raising these to power 3 and just try to simplify them, yes? But then at the end of the day, what is going to be left? So I will get an x cubed term here, an x cubed term here, so it becomes 2x cubed. But if I raise this to power 3, I will get 8x cubed. So it means that the x cubed will survive in this equation, and solving third-degree equations are not that easy, yes? But now, how can I relate this problem into this corollary? Okay, so you might somehow see the pattern. I have the sum of cubes, but 2 of them are on the left-hand side, 1 of them is on the right-hand side. Okay, so I can move them to the left. So it becomes x minus 1 to the 3. So this implies that, plus x minus 2 to the 3. And then I have minus 2x minus 3 to the 3. On the right-hand side, I will have 0. Okay? And then, unfortunately, this is negative now, but what I need is a positive sign here. Okay, so but this is easy because this is 3, so I can write it in that way. So I can write positive, and I can write negative 1 multiplied by 2x minus 3 totally to power 3, yes? If I raise this to power 3, the first one to the power of 3 becomes negative 1, which will be multiplied by this positive 1 and will give me this negative. So what I have done is right. But nobody writes it like that. I can simply multiply minus 1 inside. So then it becomes x minus 1 to the 3 plus x minus 2 to the 3 plus this becomes positive 3 negative 2x to the 3. Yes. So you need to train your eyes to see the patterns. This is the only important thing that you need to develop. This is the only skill, might be the most important skill. Okay, now can you develop? Can you see the pattern now? If I want to use this, I cannot write this is equal to 3 times the product unless one of these conditions is happening. Yes. And then this is happening actually. If you see that x minus 1 plus x minus 2 plus 3 minus 2x, what is the sum? The sum of these three, x is 2x minus 2x is gone. Minus 1 minus 2 is minus 3 plus 3 is gone. So this is 0. So that was more or less a coincidence, yes? These numbers have been fine-tuned in a way that you can use this theorem. So now what you see is that I know that the sum of 3 expressions is equal to 0. And I want to say something about the sum of cubes. Immediately I realize that the sum of cubes are 3 times the product. So this implies that I can write 3 times x minus 1, x minus 2, and then what? 3 minus 2x is equal to 0. Yes? Okay. And then what I get, that's the zero product rule. Yes, so simple. Yes, so what I can conclude that by zero product rule, either the first one is 0, or the second one is 0, or the third one is 0. But if the first one is 0, I will get x equal to 1. If this is 0, I will get x equal to 2. And if that is 0, I will get 3 over 2. So you see, this problem was simple. But of course, this problem was fine-tuned to be used so that you can use this one. But this has happened in a lot of questions, especially in contest math problems. Okay, so now the last part of these lectures, algebraic identities, I want to talk a little bit about the extensions of some identities. I will not try to be very rigorous here, so I will not probably prove all of them, because the rigorous proof of them usually needs a technique called mathematical induction. We will probably, hopefully, cover this topic in future. But so I just want to see that, okay, how, if I want to generalize some of these identities, how it will work. Okay, so let me start with the generalization of the quadratic rule. Yes, so you remember we had a plus b to the 2 is a squared plus 2ab plus b squared. Yes, then of course I also presented this identity for you. You see, this is 2, it's a binomial to the power of 2. Now you have your binomial to the power of 3. So what happens is that you have a3 plus 3a squared b. If you remember, it's 3ab squared, and then I have b to the power of 3. Okay? So far, you can see some pattern is actually going on. Here, the power was 2. I started with a to the power of 2 and finalized with the next one to the power of 2, b to the power of 2. But then in each step, I reduced the exponent of a by 1 unit, and I increase the exponent of b by 1 unit again. It's not very clear here, but let us look at here. Yes, it starts with a to 3. it ends with the other 1 to the power of 3. But then at each step, the exponent of A is reduced by 1 unit, and the exponent of B is increased by 1 unit. So here, the exponent of A was 3. In the next step, it is A2. In the next step, it is A to the 1. And in the next step, there is no A to the 0. Yes? The exponent of B was 0 here. The next step, the exponent of B is increased by 1. It is B to the power of 1 now. And then the exponent of B is increasing again by 1 unit, B to the 2. And the next one is B to the 3. So what is not easy to calculate, so are these coefficients. Okay, so for example, if I ask you, can you guess what is A plus B to the 4? I think you have some kind of a guess, a rough guess about the form of the terms, but not the coefficients. Yes. So what I can see is that it will start with A to the 4. Okay, some empty space, but then I reduce the exponent by 1 unit. It becomes A to the 3. I increase the exponent of B by 1 unit. There was no B here. It means that the exponent of B was 0, but this time it becomes 1. And then the next one is what? Is A to the 2. I decrease this by 1. I increase the power here by 1. So it becomes A squared B squared. Again, I leave some empty space here. And then the next one is A with some empty space, B to the 3. And finally, I get B to the 4. Yes? Yeah, is the pattern clear? Now, the important thing that I want to teach you is how to find these coefficients just doing it in your head. Okay, so what I'm saying is that do this. The coefficient here is 1. Assume that you want to calculate this coefficient. What you need to do is go to the previous term. This is your second term that you are interested in. You go to the previous term and see that this is power 4. You multiply 4 by this coefficient, it becomes 4. And because this is the second term, you divide by 2. So what happens? It becomes 4 times A, it becomes 4. And then when you divide, you divide by 1. That was my mistake, sorry. You multiply 4 by 1 and you divide by 1. So this becomes 4. Okay, let us do it once more. This is the third term. I go to the previous term, multiply the exponent of 3 by 4, and then divide it by the number of terms that I have written so far. How many terms I have written so far? 2 terms. So let us do it. 3 times 4 in your head, it is 12, divided by 2. So this is 6. Let us do it once more. I want to calculate this empty space. I go to my previous term, which is the third term. I multiply this exponent by this coefficient, it becomes 2 times 6, 12, and I divide by the number of terms written so far, which is 3. So 2 times 6 is 12, divided by 3 is 4. Okay? So this is the easiest way, I think, to calculate these coefficients. So let us do it once more for A plus B to the power of 5. Yes? So what should I do? If I want to raise this to power 5, I exactly know the patterns of the term. So it is A4. What is the next one? It's A5. What's the next one? It's A4B. What's the next one? It's A3B2. What's the next? A2B3, AB4, and finally B5. Yes? Let us do the coefficients again. Of course, the starting and the final coefficients are always equal to 1. So, okay, so this coefficient is 1. My goal is to find this empty space, the coefficient sitting next to the second term. Yes? So, I multiply 5 by the coefficient in the previous term, which is 1, of course. So, 5 times 1, and I divide it by 1 because so far only one term is written. So, 5 times 1 divided by 1, it becomes 5. Okay? This is 5. The next one. What's the next one? The next one is 4 times 5 is 20, and then divided by 2, so it becomes 10. Yes? And then the next one, 3 times 10 is 30, divided by 3 is 10 again. And then 2 times 10 is 20, divided by how many terms? 1, 2, 3, 4. So it becomes 5. And then finally, that's 1. So you can immediately see that I can calculate the coefficients very easily. And this is always the case. You might be able to guess. You see, the terms equidistant from the left-hand side and the right-hand side are always have the same coefficients. So for example, you see that 1, 2, 3, 4, 5 terms. This one is 1. The last coefficient is also 1. This one is 4. This is the second term from the left. This is the second term from the right. Both of them have the same coefficients. And this pattern actually appears here. Yes. So this is called the Newton's binomial expansion or formula. But this is the method that I described. If I want to write the Newton's formula, probably in more advanced lessons, you will see that this is written in this form, as sigma, then you have this formula. Okay, but I don't want to distract you by this formula right now. You don't need to know that. This is called Newton's binomial formula. Okay, so but I don't want you. I don't want to distract you by this formula yet. This is the general formula. But if you want to do it case by case, you can just do it as what I told you here. Okay. And of course, it might happen that you have different things. For example, if you want, you can do this. If you want, you can write 2x minus 3y, and then if you want to raise it to power 4, you can do that. That's also, of course, a binomial expansion, but a is replaced by 2x and b is replaced by minus 3y. So if I want to do this, I would write the first one to the 4. Yes. And then the next one, what is the next one? The next one is 2x to the 3, but minus 3y to the 1, which I don't write. But still, there is some coefficient left here. I need to come back and fix it. Yes. The next one is a little bit empty space, 2x to the 2. And then I have minus 3y to the 2 as well. And then I will go to the next step. It is 2x to the 1. And minus 3y to the 3. And finally, I will have minus 3y to the 4. Yes. So now I need to go back and fill up the coefficients. Yes, is that understandable? So what I do here is the coefficient here is 1. The coefficient here is 4 times 1 divided by 1, which is 4. The coefficient here is 3 times 4, 12 times 2 is 6. 2 times 6 is 12 divided by 3 is 4. And finally, the last one is also 1. And now I can expand and everything, yes? So I can write 2 to the 4 is 16x to the 4. That's the first step. 2 to the 3 is 8. Times 4 is 32. Times minus 3 is minus 96. X to the 3, y. Okay, here, what do I have? 2 to the 2 is 4. And then this becomes how much? Positive 9. It becomes 36. 36 multiplied by 6 is how much? 36, it's 216, I suppose. Yes, is that right? X2, y to the 2. Yes. Let me double check for, yeah. Yeah. Okay, and then this one, it's minus 27 times that 4 is minus 108 times 2 is again minus 216. X, y to the 3, and finally minus 3 to the 4 is 81 y4. And of course, you see that this is no longer valid. You see, this is minus 96, that's minus 216. The thing that I told you here, the coefficients should be the same if they are equidistant from both sides, only works if I have the starting coefficients 1 and 1. But here the coefficients of the starting is 2 and minus 3. So this is why you see that this is no longer symmetric. Okay, so that is one thing that I want you to know. This is good to know how to expand this to higher powers. Another theorem that I want to extend it for you is that, do you remember we had this pattern as well? We had a plus b plus c to the 2. We talked about this. That also can be considered as one extension of this theorem, but not to higher powers, to more variables. Yes. So do you remember what was the formula? It was a squared plus b squared plus c squared plus 2 times the first one times the second one plus 2 times the first one times the third one, and then finally 2 times the second one times the third. Yes? And it turns out that you can use mathematical induction to prove that this pattern will continue if you add to the number of variables as well. Yes? So for example, what I mean is that if you want to raise this to power 2, you really don't need to do everything from scratch. That is more or less the same pattern, but you need to learn how to write it down. So this becomes the first one to the 2, plus the second one to the 2, plus the third one to the 2, finally the last one to the 2. Yes? But then what happens? It becomes 2 times the first one times the second one, plus 2 times the first one times the third one, plus 2 times the first one times the last one. And then you go back, A is finished. I used A with B, I used A with C, I used A with D. Then I go to use B, not with A again, but from here onward. Yes, I write 2 times B times C. I would write 2 times B times D. And now everything is finished with B. I switch to C and I write 2C D. And then I am done. I hope that you learn the pattern so you can follow the pattern exactly. If I have, instead of 4 variables, if I have more variables, you can just do this. But this is on condition that you have only power 2. Yes? So that is also good to know. Another thing that I want you to know is that, do you remember we talked about this identity today? I said that if you want to multiply 2 binomials together such that they share a term in common, then what you do, you raise the common term to the 2, and then you write a plus b multiplied by the common term, and then finally you multiply a by b. Yes, do you remember? This was the starting lesson for today. But now, what happens if I have 3 parentheses? Okay, so what do I mean? X plus A, X plus B, and X plus C. Of course, you can multiply this by that, find the answer, multiply it by the next one. But if you want to do something similar, okay, I'm not proving anything, but I'm just trying to tell you what is the pattern. Okay, so you need to do that. I have a common term here, a common term here, and a common. So all of them, X is common for all of them. So how many X's are there? 3. So I would write X to the 3 first. Okay, and then the next step, I write the sum of these terms, A plus B plus C, and then I multiply it by the second power of the common term. And then I go to the next one. To the next one, I write it as pairs, A with B, B with C. So A with B, A with C, and finally B with C. And then I multiply it by single X. And finally, at the end, I have to multiply all of them. So you see, it's a very nice and quick way of expanding this in the right order. I think if I give you another example for 4, then you will realize the pattern and you can continue yourself, okay? So let me just do this one for you another time. X plus A plus times X plus B, X plus C, and X plus D. Instead of multiplying it case by case, what should I write first? You see, I have 4 binomials multiplied together, but the important thing is that all of them share the same term X. How many x's are there? So 4 of them. I start with x4. Okay, the next one is the sum of all of them. So you see only single terms appear. So this becomes a plus b plus c plus d multiplied by x to the 3. Now I consider all pairs, all pair combinations. What's the meaning of all pair combinations? I have a with b plus I have a with the next one c, I have a with the next one d. Yes? And then I go to b. I have b with the next one c, I have b with the next one d, and then nothing. Then I go to c. I have c with the next one d. These are the only pairwise combinations, yes? And then I multiply it by x2. Okay, and then I go where? I go to a combination of 3 of them, all of them. I have to write all combinations containing 3 of them, okay? So the first one is, sorry, plus a, b, c. That is one combination. The other one, I keep a and b, I go to the next one, which is d. Okay. And then I can write plus a, the other combination is cd. Okay. The other combination, so I cannot start with a anymore. A is finished. The combinations containing a are finished. The next one, I can start from b, so it becomes bcd. And no other combinations, yes? I cannot write any other combination to use 3 of them out of 4, yes? And then I close the brackets, and then I have to multiply it by x, and then finally I multiply by a, I add a, b, c, d to it. Of course, you might think that writing it is too long, but it is more systematic to write this in this form. This also has 16 terms, yes? 2 terms, 2 terms, 2 terms, and 2 terms. Okay, that is another extension I want you to know. Let me go to another extension. Okay, now let us go to another extension. So if you remember, we talked about the conjugate rule. It was a minus b, then I had a plus b, yes? This was from very old lessons, yes? It's very simple. But then last lecture, we learned about what will happen if I have the difference of cubes. So then what happens? It becomes a minus b. It is a squared. Do you remember? I need to put the product with the opposite sign. And then I have to write this one, b to the 2. Okay? Now, the question is that what can I write for a4 minus b4? What can I write for a5 minus b5, and etc.? Yes? So, if I want to use the same pattern, it turns out that it is possible. I am not going through the proof. The proof is not that hard. You can use the mathematical induction or by just direct multiplication. But then, if you want to follow the same pattern, you write a minus b here, and then you start with a to power 3 this time, yes? It was 3, you started with power 2. It was 2, you started with power 1. So you have power 4, you start with power 3. Okay? And then it becomes plus. The next one is a2. You increase the power of b, exponent of b. And then again, you decrease the exponent of a by 1, increase the exponent of b by 1. And then it becomes b to the 3. And then you stop. Of course, it is possible in this special case that you can continue more. So for example, you might say that why shouldn't I do this? In principle, a to the 4 minus b to the 4 can be written by conjugate pattern as a squared minus b squared times a squared plus b squared. And then again, this you can use the conjugate pattern to factorize this. Of course, even this is better here, but what I am saying is that this is also correct, okay? But this pattern only works for the 4 here, but this pattern that I am talking here is working for all integer powers, natural powers of a. So for example, here, if I want to do the same thing, it becomes a minus b, a to the 4 plus A3 B A2 B2 AB3 and finally B4. And you can continue this list. Yes? Okay. Here now we had another one. So if I want to talk about one more here. So if you remember, if I start with the same thing, a squared plus b squared, I cannot factorize it more if I want to use the real numbers, okay? So no factorization is longer available here. But if I have a3 plus b3, then you remember from the previous lecture that it is a plus b, a squared minus ab plus b squared, yes? Now it turns out that a4 plus b4 doesn't work, okay? But again, a5 plus b5 will follow the same pattern. Yes, what does it mean? It means that you can write a plus b, and then you can write a4, a3b, and then you can write a2b2, and then you can write ab3, and you can write b4. But the point is that you need to change the signs alternatingly. So the first one starts with positive, the next one is negative, positive, negative, and positive. So what is the moral that we can take here is that for even powers and positive signs in between, we don't have any pattern, okay? But so it might happen that we can still factorize it. In the future, I will talk about that. For example, this expression, you can factorize it more or less if you allow for square roots and things like that. But here, if I have the positive sign in between, and I have odd powers, then I can use the pattern. Yes. For example, can I write something for a6 plus b6? Yes, I can do something, but not this pattern. Yes. So by the way, if I want to write something for this, I can write it as a2 to the 3 plus b2 to the 3. And then, of course, I can use this formula here to factorize it, but I have to replace a with a squared, b with b squared. That's not my goal, okay? So that's not my goal. If you want to follow this pattern, then the exponent has to be odd and the sign has to be positive, yes? I'm not saying that for this you cannot do anything. You can do it. Actually, you can use this formula to factorize that. But that's not my goal. If I want to use this pattern that I mentioned here just now, for example, you cannot use this pattern for here, but you can use the pattern for a to the 7 plus b to the 7. Yes? So you can write a plus b, yes? And then you have to write a6, a5b, a4b2, a3b A3B3, A2B4, AB5, and finally B6. And then start changing the signs alternatingly. Positive, negative, positive, negative, positive, negative, and positive. Yes? So, yeah. Of course, I will talk a little bit about these things more in the lectures related to factorizing polynomials, but let us, know a little bit about this at this stage. And there is one more. Now, what happens, I want to write something for this as well. So now here I have A, I have minus B, okay? But I have an even power, okay? So you see that for even powers, then you can have two of them, of course. Yes. So if I have this situation, I can still calculate this like that. A4, for example, minus B4. But then you need to remember, this is a little bit strange. This is negative, you put positive here. Yes? And then you follow the same pattern and change the signs alternatingly. So let us see that. A plus B, and then you have A3, you have A2B, you have AB2, and finally you have B3. The first one is positive, negative, positive, negative. Yes? So you see that for A4 minus B4, you have both this formula correct and that formula correct. Okay, so let us check that this is really working. Okay, so if I want to start, I can start from the right hand side. You multiply this inside, so checking. I multiply this inside, so it becomes a4 minus a3b plus a squared b squared minus ab cubed. And then finally you multiply that, ba3 minus a squared b squared plus ab cubed, yes, minus b4. And let us see, hopefully that everything is going to work. Yes, this one and that one are opposite, they cancel. A squared, b squared, positive, negative cancel. Ab cubed, oh, okay, I made a mistake. So A3B negative is canceled with this one. That's right, I made a mistake. And minus AB3 is supposed to be canceled with that one, but everything is now in order. And what is left is A to the 4 minus B to the 4. And that is exactly what you have. So remember, for A4, for example, minus B4, you can either write that one or that one. So the important thing here is that this type of pattern will work if you have the negative sign between an even exponent. So for example, if you want, you can write something for A6 minus B6 as well. You can write something for A8 minus B8 as well. But you are not allowed to start with A. Of course, let me write two things for you. If you want for A6 minus B6, you can use this pattern. Start with A minus B. Then what can you do? You can write A5 plus AB, plus A4B plus A3B squared plus A2B3 plus AB4 and finally B5. This is one way of dealing that. So I am keeping the sign the same. But if you want, you can choose this pattern. You can write A plus B, the same thing, but you have to change the signs alternatingly. Yes. So it becomes A5 minus A4, B plus A3 B squared minus A squared B3 plus A B4, yes, and minus B5. Okay, so it's very important for this pattern, I should have even powers. But for this pattern, it doesn't matter if this is even or it is odd. Okay? Okay, these are the extensions about the identities that I wanted to talk. Might be I will give you some examples in the problem sets, and then I will probably talk a little bit about the application of them. Yeah, so there is something left here now. Okay, there are three formulas I want you to prove. I want to prove it for you, but I can just do two of them here, and then you can do the other ones yourself. But I want you to see the trick. The trick is really nice, okay? So here, so might be you have seen this before in your elementary lessons. So this is 1 plus 2 plus 3 plus 4, and I continue up to n, yes? This is a simple sum. It's a very famous sum. It's an arithmetic progression. So you have seen how to calculate this sum probably when you were learning about arithmetic progression, okay? And then I hope that you remember the formula. The formula is this, okay? And then there are other formulas. So you can calculate the sum of the squares. This is also a question. The question is that, is there any closed formula similar to this? Can I write a simple formula for this expression? Can I write a simple formula for this expression? Yes. And then I can write a formula for this expression. So these are the questions. Of course, you can continue this list. It turns out that there is a very nice systematic way of solving all of these problems. Of course, you need to do it step by step. For example, if you want to answer this one, you need to be patient, do this one, do this one, do that one, and then use all the results to answer the last one. So in principle, you can continue this list for any positive integer that you can see as the exponent. Yes, that's the goal. So it might be you have seen one type of proof for this. Do you remember? So one type of proof for this, in this case, that might be you have learned when you were dealing with arithmetic progression. It's called it Sn. And then you say that, okay, instead of writing it in this order, I can write it in the other order from here to here, from the last number to the first. Of course, it is completely clear that nothing will change. This sum is still the same sum. And then you can add both sides together. Then it becomes 2Sn. Then n1, it becomes n plus 1. 2 plus n minus 1, it also becomes n plus 1. And then you can continue until the last one. N plus 1 is again n plus 1. And then you can see that all of them are n plus 1. How many times? N times. So then it means that 2Sn is equal to n times this. And then you divide by 2. Okay? I did it very quickly because hopefully you have seen this type of proof for this sum when you were dealing with arithmetic progression. Okay, that's completely valid. That's completely okay. But now I want to introduce you another type of calculation, another strategy to tackle this problem. And the good point about this strategy is that it will allow you to calculate this one, this one, this one, etc. Okay, so how we should deal with that? Okay, again, let me concentrate here. First, I want to say that, okay, let us calculate this one first. K squared minus k minus 1 to the 2. It's a little bit tricky, but you need to be patient to see the result. Then you will appreciate it, okay? So let me calculate this one for some k, any k that you like. It's easy to calculate because this is k squared. Then I have what? I have the quadratic pattern. So it becomes k squared minus 2 times the first one times the second one plus this. So then I imply this negative sign inside the brackets. So it becomes k squared minus k squared plus 2k minus 1. Yes? And then this k squared and that k squared are canceled. So what is left is 2k minus 1. Agree? So what can I write? So what I got is that k squared minus k minus 1 to the 2 is equal to 2k minus 1. If somebody asks you, is that a correct expression? You would say yes, and that's the proof. It's very simple, yes? But this is an equality valid for all possible choices of k, okay? Let me choose k. This is valid for every possible k, so let me choose k to be 1. Okay, so then how this will read? It will read 1 to the 2 minus 0 to the 2 is 2 times 1 minus 1. Agree? I proved that this formula is valid for all choices of k. This is the simple proof of that. And now I am saying that let me choose k in this relation. What happens? This becomes 1 to the 2. 1 minus 1 is 0. So this becomes 0 to the 2. And then it becomes 2 times 1 minus 1. I intentionally write 1. Okay? Let me choose k equal to 2. Let us see what happens. If I choose 2, then it becomes 2 to the 2 minus 2 minus 1 is 1, 1 to the 2. Yes? On the right-hand side, I will have this 2 multiplied by the k. But the k has chosen to be 2. So this becomes 2 times 2 minus 1. Agree? Let me write something more for you. So k equal to 3. Let me choose k equal to 3. Then it becomes 3 to the 2 minus 2 to the 2. Agree? Because k is 3 in this case. If I put 3, it becomes 3 to the 2. If I put 3 here, 3 minus 1 is 2, 2 to the 2. And on the right-hand side, it becomes 2 times 3, and again, minus 1. Yes, I agree? Okay, I can continue this list. For example, I can write k equals to n minus 1. If I choose k equal to n minus 1, let us see what happens. I replace k with n minus 1, so it becomes n minus 1 to the 2 minus k is n minus 1, n minus 1 minus 1 is n minus 2 to the 2. On the right-hand side, I have 2 times my k. My k in this case is n minus 1, so I write it in this order, and then as usual, here I have minus 1, minus 1. And then let us do the last one.
Yes? So k is now equal to n. I choose k to be n. Then I would see that it's n squared minus n minus 1 to the 2. The right-hand side is 2 times n minus 1. Okay? Okay, take your time to digest what I have written here. So I proved an identity very simply. What I have written here on the board, in each line, I am choosing a different value for k, k1, k2, k3, and I rewrote the expression, this expression, for those choices of k, yes? And the point, the nice and interesting thing here is that the strategy is to do this. I add all these things together. Let us see what happens. Here, 1 squared and minus 1 squared are cancelled. Yes? Here, minus 2 to the 2 and 2 to the 2 are cancelled. Yes? Here, this 3 to the 2 will be cancelled, but what is coming here? And if you continue in this way, this will be cancelled by that one. This is already cancelled with what is here. And then what is left here, if you see, this is left, and finally this will be left. But this 0 to the 2 is just 0, so we don't need to bother. What I need to see that from this list, I have only n squared survives, yes? This kind of adding things, sum is called the telescopic sum, yes? So, but what happens on the right-hand side? On the right-hand side, I have a factor of 2, a factor of 2, a factor of 2. You see this factor of 2 is common for all of them. So I can take this factor of 2 out, and from here 1 is left, plus from here 2 is left, from the next one 3 is left, and I can continue from here n minus 1 is left, and finally n is left. Yes? And then, of course, I have minus 1, another minus 1, up to this minus 1. How many of them are there? N, yes? This is the first row, second row, third row. The last row is the nth row. So I have 1 here, minus 1 here, minus 1 here. So it becomes minus n. Yes, agree? Minus 1 is minus 2. Minus 1 is minus 3. Up to here, it's minus n. Yes? But do you see, this is exactly the question mark. I am supposed to find a formula for this. So it means that this is my question mark. So I am looking for that question mark. That is easy to calculate now. On the right-hand side, on the left-hand side, you have n squared. On the right-hand side, you have 2 times the question mark. And I have 1 minus n here. Yes? But I'm supposed to find the question mark. So I move minus n to the left. It becomes n squared plus n is equal to 2 times the question mark. And then the question mark is this expression divided by 2. And then you see, if I factor n out, this is exactly the same formula. Okay, of course, you can see that this way of calculating that simple thing is more complicated. But it has this advantage that this method will stop if you want to use the same method to calculate the next one, to calculate the third one. But this method has this advantage that you can use the similar ideas to continue calculating all the formulas for this list. Yes, I will do the next one for you, and then probably I will give you some exercises to do some other ones yourself. So let us do the next one as well. Okay, the point is that the starting point for the first one was k squared minus k minus 1 to the 2. But if you want to do similar ideas for the next one, you have to start with k to the 3 minus k minus 1 to the 3. Okay, so let me clean this part of the board. Let us do it together. Okay. Now I have this in my list. I want to calculate the second one. What I am trying to say is that your starting point should be considering this, k to the 3 minus k minus 1 to the 3, yes? It is easy to calculate now. K to the 3 is just k to the 3 minus. So if you remember, we had this binomial theorem, or if the previous video we know how to deal with if I have a power of 3. The first 1 to the 3, 3 times the first 1 to the 2 times the second one, which is minus 3k squared. 3 times the first 1 times the second 1 to the 2 is 3k, and finally I have minus 1. And then let me open the bracket, so it becomes k to the 3 minus k to the 3 plus 3k squared minus 3k plus 1. Yes? And then this k3 and that k3 are cancelled. So let me write the formula that I will need. So k to the 3 minus k minus 1 to the 3 is equal to, what is left for me is 3k squared minus 3k plus 1. This is the formula that will play the role of that formula for this case. Yes? But the idea is very similar. So the idea is very similar. How? Here I want to use this formula here. So if you don't mind, let me write the formula here on top in front of our eyes. Okay, so this is my starting formula. Again, you know what to do. You used k equal to 1. Exactly the same method. I put 1 here. It becomes 1 to the 3, 0 to the 3. It becomes 3 times 1 to the 2 minus 3 times 1 plus 1. I intentionally don't calculate them. Okay, so what about k2? If I put k2 here, it becomes 2 to the 3 minus 1 to the 3. It becomes 3 times 2 to the 2 minus 3 times 2 plus 1. Let me do one more. So this becomes 3 to the 3 minus 2 to the 3. It becomes 3 times 3 to the 2 minus 3 times 3 plus 1. Yes, is that understandable? Here I have this formula for all possible values of k. I am choosing k to be 3 and I am plugging that 3 here. So it becomes 3 to the 3 minus 2 to the 3, and then instead of k I put 3, so it becomes 3 times 3 to the 2 and minus 3 times 3 and then plus 1. Yes, and I continue as before. Finally, let me just skip the previous part, so I just can calculate it directly for n, because you know what's going on. If I put n, it becomes n to the 3 minus n minus 1 to the 3. On the right hand side, it becomes 3 times n squared minus 3 times n plus 1. Yes? The idea is exactly the same. I add all of them. Add all of them side by side and term by term. So again, the same story. This one and this one are opposite signs. They vanish. This will vanish with this one. This will vanish with the next one. This is already vanished from the previous one here. And what is left again is that one and this one. Yes, but 0 to the power of 3 is just 0. So what is left is just n to the 3. Okay, let us do this one here. If I add this one, and this one together, you see all of them share a factor of 3. So I can take that 3 out. And then what is left from this is 1 to the 2. Plus what is left from here is 2 to the 2. And what is left here, 3 to the 2, until I reach to the last step, which is n squared. And you see that this is exactly my question mark now. In question mark here is this. Okay, but now, of course, I have some leftovers now. Here, and this one, all of them share a factor of minus 3. So I can take minus 3 out. But let us see what happens. 1 is left. The next one is 2. The next one is 3. And then you continue up to n. And then you have 1 positive 1, 1 plus 1, 2 plus 1, 3 up to here. It's n. Okay? So what is left, what is the only question mark here for you is this one. Agree? This is your question mark. Because this is no longer a question for you. You already answered that. This is exactly 1 plus 2 plus 3 plus n. So I know that this is this expression. Yes? So everything is in order. I am looking for this question mark. So let me do this here on the board. So I would write n to the 3 is equal to 3 times my question mark minus 3 times this expression, yes? So this becomes 3n, n plus 1 divided by 2. And I have an extra n at the end. My goal is to find a question mark, so I move these two terms to the left-hand side. So it becomes n to the 3 plus, it becomes positive, and then I move n to the left. I am left with 3 times the question mark. Okay. So let me simplify this expression for you. Here, I can take a common denominator. So this becomes 2n3. This is just 3n, n plus 1. And this is minus 2n is equal to 3 times the question mark. Yes, understandable? So instead of n3, you can write 2n3 divided by 2. Instead of minus n, you can write minus 2n divided by 2. So at 2, 2, and 2 are the common denominators, so I need to add this one with that one with that one. Yes? But then let us see what happens. Here n and n are in common, so I can take n out. From here, 2n squared is left. N is gone, 3 is left, and n plus 1 is left. So I multiply 3 in, so it becomes 3n plus 3. And n has been taken out, so it's minus 2. And then I divide it by 2, it's 3 times my question mark. Okay? But then this becomes n. So let me write it implies that. So this becomes n, 2n squared plus 3n. 3 minus 2 is 1. Divided by 2 is 3 times the question mark. But I am looking for question mark, so I divide everything by 3. So what I get is my question mark is this fraction divided by 3. So this becomes n times 2n squared plus 3n plus 1. This fraction divided by 3, it becomes 6. So this is your answer. But it turns out that you can factorize this expression, so it becomes n times n plus 1, 2n plus 1. For the time being, that's okay, just write it like that. Then the next lessons, I will start teaching you how to factorize polynomials. But now you can convince yourself what I have written here is correct. N times 2n is 2n squared. N times 1 is n. 1 times 2n is 2n. N plus 2n is 3n. And 1 times 1 is 1. Yes, so what you get is this nice formula. So you see, we were able to use the same strategy to find this formula. So 1 to the 2 plus 3 to the 2 up to n to the 2 has a nice formula. It is n times n plus 1 times 2n plus 1 divided by 6. Yes? Okay. And then you can do the same strategy. I will ask you to do them in the exercises to calculate the same sum, but for powers of 3, okay? Okay. So for the time being, I think that's enough for discussing about identities. Might be we can talk a little bit more or even bring a lot of problems in, but we need to continue to learn new subjects as well. So I will stop the discussion of identities exactly here, and I will start the next lesson of factorizing the polynomials and the techniques that we need to factorize the polynomials from the next lesson. Okay, I will upload a problem set concerning related to this material that I covered today, and I will upload the video for the solutions of those problems next Wednesday. Okay, thank you.